This presentation will focus on pesticides and the environment. The information can be found in Chapter 7 of the National Pesticide Applicator Certification Core Study Manual. If you remember, during one of our first presentations, we talked about all the research that must be performed before a pesticide can be registered. A recap of a few things the manufacturers want to find out include: does the pesticide effectively manage the pest? Does the pesticide damage plants, those being treated for the pest or other plants in or near the area? And what happens to the pesticide after it's applied to the site? These discoveries help to determine not only whether or not the pesticide is safe to use, but also if there are ways to reduce the risk of exposure or contamination to the environment, and the types of precautionary statements and requirements to include on the label or labeling to guide the user. Here's an example of a label section instructing the handler to consider weather conditions to avoid drift and to be aware of the environment in and around the treatment site. It gives examples of residential areas, bodies of water, threatened or endangered species, and non-target crops as being especially sensitive to the pesticide. Take a moment to think about the areas surrounding your treatment sites that might be impacted by the pesticides you use. How many of you will be applying pesticides at or around schools or parks? What about hospitals or other facilities where there might be ill or elderly people? Will you apply pesticides near gardens or waterways? Do you ever notice bees or other beneficial insects in the area? If you notice, there are suggestions on the bottom of the slide, ways you can reduce the risk of contaminating the environment. Notification about applications are very helpful and allow people to make informed decisions on their own safety. For example, providing schools 72-hour advance notice about applications on or adjacent to the school site enables the school to notify parents of children who might have asthma or other health conditions. Buffer strips are untreated areas between the pesticide and the sensitive area, such as along a river or stream, to reduce the likelihood of drift in the water of any pesticide that might be toxic to fish. Previewing the environmental hazards section of several labels might give you time to research products to find out if one is less harmful to the environment than another. If they're equally effective in managing the pest, you might be able to choose and use the one with fewer environmental risks. Finally, as we've talked about earlier, integrating different pest management strategies can reduce your reliance on the use of pesticides for your only option managing the pest. I want to take a moment to expand a bit on pollinator protection. Here are a few questions to ask before you mix and load a pesticide that has the potential to negatively impact bees. Are bees or other beneficial insects present or near the area? Are there beekeepers within 5 to 10 miles? Are there flowers on the plants near the treatment site? What are the weather conditions and how does the pesticide react or break down in these conditions? Cloud cover, moisture, extreme heat or cold are all examples. Is there an area where the pesticide you're applying is puddling? Are you applying a dust? Is the pesticide persistent? How long will it remain in the plant? And most importantly, is there a pesticide you can use that isn't toxic to bees? And how can you implement IPM into your pest control program? You might also notice warnings about plant back restrictions, grazing restrictions, pre-slaughter intervals, or statements about toxicity to domestic animals on the labels. These types of statements are based on findings of the pesticides being potentially harmful to different crops or plants, wildlife, pets, or livestock. Once you've selected a pesticide, it's very important to survey the area again before applying the pesticide. Something might have changed since the last time you looked. One of the factors impacting a pesticide's potential to contaminate the environment is its solubility. Solubility is a pesticide's tendency to readily dissolve in water. While this certainly seems advantageous when you're mixing and applying pesticides, it can be a disadvantage if you have a spill in the soil, it rains shortly after the application, or the area is irrigated. Water-soluble pesticides are more likely to travel with other liquids. Wherever rainwater goes, for example, if it seeps into the soil or runs off into a river, the pesticide will travel with it. You might work with a pesticide that's been detected in Kentucky's groundwater and is known as a groundwater contaminant. Now let's look at the wording on this label. Notice it mentions risks in the areas where soils are permeable, particularly where the water table is shallow. This is problematic with Kentucky's karst soils and sinkholes. If a pesticide handler was planning to use the pesticide with the environmental hazards listed on the previous slide in this area, what safety measures would you recommend? This is a marshy area and therefore groundwater and surface water contamination is possible. Also, it doesn't look like it's a good time to apply the pesticide. The potential for drift into the lake or pond is likely as well, which could also kill fish. The best safety measures could be to use mechanical weed control, a different pesticide that isn't hazardous to water sources and fish, and to always focus on the weather. Some people might even say it isn't necessary to control these weeds because they provide habitat for birds and other wildlife. When we looked at the photo in the previous slide, there were several concerns about the application near bodies of water and the potential for contamination of wildlife and fish that might be in the area as well. Additional things to consider and questions to ask are, how likely is the pesticide to leach or percolate through soil? If a pesticide percolates through soil, it moves down through the soil. When something leaches through soil, it filters through and pulls the nutrients along with it. The soil type and geology play huge roles. Question: think about sandy soils, clay soils, or soils with a lot of organic matter. Would pesticides more rapidly filter through sandy, clay, or soils with a lot of organic matter? The depth of the groundwater is also key. If the groundwater is shallow or you're near a sinkhole, you have a greater likelihood of the pesticide reaching the groundwater faster. Should you spill a pesticide in the soil, you should irrigate it or watch for rains shortly after the application and before the pesticide has a chance to degrade. So you've heard of the word absorption. This is not a typo on the top of this slide. The word actually is adsorption. It's defined as the binding of chemicals to soil particles. Clay and soils with organic matter increase binding, which in effect decreases the potential for the pesticide to move through the soil. A good way to remember the definition of the term is to think about when people are making clay pottery. They add liquid to the clay and it sticks to the clay. Even though I just mentioned pesticides have a tendency to bind to clay particles, which slows down the potential for leaching or filtering through the soil, it's still important to promptly and correctly respond to pesticide spills in all types of soils. We'll look at spill response in another presentation later, but in the meantime, I want to touch on how to correctly clean up a liquid pesticide spill in the soil. One of the reasons it's imperative to quickly and correctly clean up spills in the soil is because some pesticides are extremely persistent. Think of that word, persistent or persistence. What does it mean to you? Something that keeps hanging around? Something that doesn't quit? When we talk about persistent pesticides, it's very similar. A pesticide's persistence is the amount of time it stays around or is still active in the environment before it degrades or breaks down. And it's not always a bad thing. In fact, you want a pesticide to be persistent enough to control the pest. However, you also need to know about its potential to cause harm to sensitive plants or animals in the area. There are also concerns about pesticides that persist in the treatment area for a long time, especially if you're rotating crops, building schools, or homes in the area in the near future. Will there still be pesticide residues in the soil? If so, are the pesticides still existing at levels of concern? That brings us to the topic of half-life. A pesticide's half-life is the approximate amount of time it takes for half of the product to break down, giving us a general idea about how much could potentially remain in the environment. We'll touch on this briefly, but I'm also providing you with a handout from the National Pesticide Information Center describing the half-life concept in more detail, which is attached to another 2-page handout listing various active ingredients and their half-lives in soil. We just looked at half-life comparisons in soil. However, a pesticide can have a different length of time it degrades in the water, air, or inside of a plant. There are also factors that affect the amount of time it stays in the area. For example, the sun, water pH, microbes in the soil, etc., could help it break down even more or faster. When you apply pesticides, it's also very important to study the wind speed and know what's downwind of the treatment site. As you know from working in Kentucky, during most days, wind can be an issue and can suddenly change direction as well. What's interesting is you actually want a bit of breeze to help you determine what's considered downwind of the site at that day or that time. This will help you make an informed decision on whether you should apply the pesticide at that time, if there are adjuvants you can use to minimize drift, or if there's a way to create a buffer zone area. In addition, when the wind speed is low, such as between 0 to 3 miles per hour, the air is stagnant and it's very hard to determine the wind direction. The optimal wind speed is 3 to 10 miles per hour. However, follow the pesticide label for more accurate instructions, as some pesticides are extremely volatile and you might have different wind speed requirements unique to that pesticide. Now let's take a look at spray pressure, droplet size, and distance from the treatment site as factors that can contribute to drift. This is a photo of water through the equipment before pesticides were added. The researchers needed to check the equipment and nozzles to determine if they needed to make adjustments before the application. This is an extremely important step. I like this photo because you can see different droplet sizes and what's happening. As you'll see described on this slide, larger droplets are heavier, equaling decreased drift potential. Smaller droplets are lighter, equaling increased drift potential. Similarly, you can also look at the thickness or viscosity of the droplets. Thicker droplets would be heavier and tend to drift less as well. Increasing spray pressure equals smaller droplets equals an increase in drift potential. Distance from the ground equals a greater likelihood of drift because wind has more area to pass through. Volatility is a little different. It's the tendency of a pesticide to turn into a gas or vapor. It's important to note that not all pesticides are volatile, and therefore not all pesticides will vaporize when temperatures rise. However, those pesticides that are volatile, such as dicamba, can vaporize and drift off the site. This is most likely to happen as the temperature gets hotter, when winds pick up, and you have dry weather. Now a quick quiz. Here we have a man spraying a pesticide up in the tree canopy. He's using a high-pressure sprayer and producing fine or ultra-fine droplets. What are your concerns with this situation? What would you do differently? What would you do before you sprayed? Note the lack of gloves, wide-brimmed hat protection, and the person in the background walking in shorts. You might notice a warning about temperature inversions on some of the labels of the products you use. This label states application should not occur during a local low-level temperature inversion because drift potential is high. Temperature inversions can be a difficult concept to describe, so I have a few slides and a short video clip to demonstrate it. Think about smoke rising. During normal weather conditions, the air is moving vertically, diluting the material. During normal weather conditions, pesticides become less concentrated in this process and they dissipate, just like the smoke rising. During temperature inversions, a layer of cooler air is trapped by a layer of warmer air above. At night, the ground level temperature cools faster than the air above it. Pesticides can become trapped under the layer of warm air. Once the wind or breeze picks up, pesticide vapors can travel for long distances and drift and settle in other areas. This is a really good pair of photos from the same area at different times of day. You can really see the temperature inversion layer in the bottom picture. Temperature inversions often occur when the sun sets and then they last until morning. They're common on nights with little to no cloud cover and light to no wind. In summary, here are a few factors that contribute to contamination of the environment. Soil type and depth of water table, the time of year and weather conditions, pesticide formulation and type of equipment, droplet size and spray pressure, And lastly, the pesticide applicator's knowledge and views of the importance of working safely with pesticides, which we'll continue to cover in the remaining sessions of this course.